Hello, people of AGU. It is 1 degree Fahrenheit or minus 17 C here outside my cabin in Fairbanks, Alaska. I'm Eric Peterson, a postdoctoral researcher at University of Alaska Fairbanks Geophysical Institute, and I'm working with Regina Hawk on this project concerning the Kennicott Glacier, its debris cover, and ice cliffs. This is what a debris-covered glacier looks like. The surface is rough and hummocky, and you have these segments of steep exposed ice. These are these darker regions. The ice is dirtied by a little bit of silt which sticks to the surface, and we call these ice cliffs. We want to learn a little bit more about ice cliffs because the debris on debris-covered glaciers, when it gets above a certain thickness, it slows the melt of the ice beneath relative to a clean, non-debris covered glacier. However, these low albedo ice cliffs are melt hotspots, and to some degree, they offset the reduction in melt caused by the debris. So we want to understand those better. Why are debris-covered glaciers in general important? Well, they're numerous. In Alaska, in the high mountain Americas, and in high mountain Asia, where they provide a freshwater resource for millions of people, as well as a freshwater resource for growing a lot of food. They're also important to understand for contribution to sea level rise and the cryosphere's response to a warming climate. We're going to see more alpine glaciers having growing debris cover, and we have to understand how these growing debris covers respond to climate change. So zooming back into the issue of these ice cliffs, I'm working on this project trying to address some basic questions about them. How does the debris cover and the ice cliffs moderate the energy balance and melt of debris covered glaciers? More fundamentally, how do ice cliffs form, persist, and evolve? What are the major drivers at play here? If we can attain a new understanding of these processes, how can we incorporate those into future models of glacier melt? To do this, we're doing a field project on the Kennicott Glacier, which is in the Wrangell St. Elias Mountains in Alaska, near McCarthy, Alaska. The Kennicott Glacier is a large valley compound glacier, which has numerous medial moraines which coalesce to form a continuous debris cover in its lower ablation zone. In this project, our methods include the installation of a weather station on the debris covered part of the glacier to get energy balance data in situ. We're also measuring debris thicknesses, setting up ablation stakes, and general observations of ice cliffs in the field and with remote sensing data. We're also using time-lapse imagery to monitor the cliffs over the course of a melt season. And this is going to be what I'm going to talk about primarily in this presentation, is the monitoring of ice cliffs through time-lapse photography. I will touch on these other methods briefly. I should also mention that we have a collaboration with the Chinese Academy of Sciences, which has a decade-long funded project on the Kennicott Glacier in terms of monitoring with off-glacier weather stations, ablation stakes across the surface, not just the debris-covered section, and other installations. Unfortunately, because of the COVID-19 pandemic, our colleagues from CAS were unable to make it to the Kennicott this year. And we were able to do our best to help them out by visiting some of their installations, check on them. While I'm on the subject of COVID-19, I really want to thank a lot of people who made this work possible, including Jamie Warwick of UAF. She's our safety officer, helped a lot with COVID-19 mitigation and safety planning. Martin Trufer and Jason Geck provided a lot of help with logistics. The Wrangell Mountain Center, based out of McCarthy, Alaska, helped a lot with logistics in the field. And we just had an amazing field team of volunteers, including graduate students from UAF. We also had a graduate student from University of Maryland, Baltimore County, Nicole Trenholm. She was really active in producing field vlogs. You can see some examples of the videos here. You can scan the link that you see on the video and go to those. We did field work this summer in June, July, and September of 2020. You can see this map of installations in blue and green are Chinese Academy of Sciences installations, which are distributed across the glacier. And in red are our installations, which are really just down in the lower ablation zone where you have that continuous debris cover. I'm going to show you now a little info about our weather station we set up. This weather station is a full energy balance weather station set up out in the center of the debris. We have temperature, relative humidity, 2-3 meters, wind speed and direction from a cap anemometer as well as a sonic anemometer, so we can get good constraints on turbulent fluxes, and our 4-component radiation. I'm not going to show this data here today, but we will have this to use for energy balance modeling as we continue with this project. We also have temperature profiles in the debris layer so we can quantify the conductivity of the surface debris. And you can see an example of some of our temperature records for that here. This pit that you can see with the temperature profile is about 25 centimeters thick. We got 101 pits that we dug across the surface of the glacier to measure the debris thickness. Our mean thickness that we see is about 16 centimeters. Of course, the debris thickness increases as you go down glacier towards the terminus. And we never really saw debris thicknesses greater than 50 centimeters, at least at the locations where we dug. Now I will get into the aspect of this project which I'm most excited about right now, which is the ice cliff monitoring aspect. We set up a few time-lapse cameras on the glacier. You can see this box here has a Canon camera in it, trained on this ice cliff, which is facing towards the west. On this ice cliff, we also installed an ablation stake. That is, we drilled into the ice horizontally through the cliff and inserted a series of PVC segments, 1.5 meters each, so that we can watch as those segments melt out in real time with the time-lapse photography and quantify exactly how much is this ice cliff back wasting. I'm going to walk us through the time-lapse. Near the top of the cliff, a cavity starts melting out. Here we install the ablation stake in the center of the screen. The melt stream at the base of the cliff you can see fluctuating throughout the day. Over here you can see melt streaks forming on the cliff face, also boulders melting out, popping down. Take a look at our ablation stake. You can see the segments melting out, 1.5 meters each. Over on the left of the screen, you can see this debris shelf. There's just been this orange rock delivered to it from the top of the ice cliff. And if you watch it over time, you can see it migrating from right to left. It's like the shelf is a debris conveyor belt, which occurs as the ice cliff faces back waste towards the right. It's a relative motion sort of a thing. See it moving towards the other face. Back on the center of the cliff, a big boulder is melted out. It's about to drop down. There it goes. Our orange rock has nearly completed its travel, and there it goes. It drops down. It's off of the shelf. Where our end glacial cavity used to be, there's now a new tiny debris shelf that has formed. If you look down to the base of the cliff, you will also see that the incision of the melt stream has created a deeper overhang than was seen at the beginning of the season. Meanwhile, our ablation stake has melted out at this point 1, 2, 3, nearly 4 segments completely. So the degree of back wasting that we see with the ice cliff over a season is actually quite substantial. There's 8 meters of horizontal back wasting between June 19th and September 3rd. When we geometrically correct for the pitch of the cliff, that comes out to 17.5 centimeters per day of back wasting. We have ablation stakes by the weather station where we're getting surface lowering, just raw surface lowering of 1 to 2 centimeters per day under 6 to 20 centimeters of debris. So already right off the bat, that's indicating that based off of our point measurements, that's up to 16 times as much melt on the ice cliff as you're seeing under the debris in the same general area. We can also compare what the ice cliff looks like at the beginning of the season to the end of the season. Here's the ice cliff on June 15th and on September 4th. You can see that in general, the cliff looks largely the same in terms of its shape. The shape of the crest changes a bit as it backwastes through the topography, and you can see a deeper incision of the melt stream at the base of the cliff through time, as well as this thin overhang, which melts more substantially than the faces around it. If we zoom in at the crest of the cliff, we can see how this cavity, which I pointed out in the video, as it melts out, it gathers the debris on its lower lip and creates a debris shelf, which persists even as the cavity goes away. Zooming in towards the left on this steeper debris shelf, I won't belabor the point because I discussed it while we were looking at the video, that this is like a debris conveyor belt. But also notice how it's planar. It's like a linear debris shelf, which is continuous. It fully divides the ice cliff into two different ice faces at this area. And we see shelves with this geometry on ice cliffs across the glacier. They're quite common. And I think that these may be caused by crevasse traces indicated by these red arrows, which melt out of the ice cliff face, and micro porosities gather the debris, and it's able to create a debris covered shelf such as this one. This image of a debris covered shelf is actually one that permitted us to continue traveling on the glacier in an area where the cliffs were so high and substantial and the topography so rugged, we weren't sure if we were able to continue walking further. And this steep shelf, which divides this cliff into two faces, allowed us to continue traveling. I'm going to show you time lapse now from a second site. This is a smaller set of ice cliffs. These are only on the order of 2 or 3 meters tall, whereas the one I was showing previously is about 10 meters tall. This is a tongue, a debris covered tongue of ice sticking out from the ice cliff. And we actually walked down this at one point when we were traversing this part of the glacier, turned around and saw that the stream, which commonly we see at the base of these ice cliffs undercutting them, had undercut this ice tongue, and it was in fact an arch. And so I thought that was an interesting feature to look at with time lapse. If you keep your eye on the ice tongue, you can see it melting back at an accelerated rate compared with the ice cliff surrounding it. Eventually, the ice tongue will ablate completely away, and those two ice cliff faces will start to merge. If you look here, you can see how the debris is diffusing across the surface of the glacier in response to differential sub-debris melt. In this case, the debris is diffusing to such a rate that the ice is getting exposed, and we are in effect seeing the birth of a small ice cliff. So to sum up what we're seeing with ice cliff monitoring, we see that moderate to large size cliffs don't change a lot in their gross morphology, whereas smaller features on the cliffs and small cliffs can change substantially. For example, that ice tongue that we see in the second video melts away completely. Those cliffs merge. And we can see that in glacial structure can affect the evolution of ice cliffs. The melt out of end glacial cavities and crevasse traces can produce structures such as these debris shelves that can split a single cliff into multiple cliffs. We also see some tantalizing hints that melt stream incision can play an important role, perhaps, in the evolution and sustenance of these cliffs. But going forward in this project, I'm going to be combining this with our energy balance data, as well as more morphological analysis. And I hope y'all will stay tuned for the future results of this work. And I look forward to speaking with y'all in the Q&A session. Thank you very much.